All right, here we are again. So, again, as we think about dramatic changes, in 5 years after the Massachusetts 2016 legislation, offshore wind commitments increased by a factor of 20. It's just an incredible number. You know, the most incredible number I've ever seen was at the end of 2015, the leases went for $1 an acre. That was right after Cape Wind lost its power purchase agreement and right after we brought in a new governor in Massachusetts and everybody thought the days of renewable energy were over. By 2022, the prices were going for $10,000 an acre, and some of the lease areas in the New York Bight were selling for $1 billion. Now, I'm not sure that's anything to be proud of necessarily. And people said, you know, this gets so expensive, the leases are going to cost more than the wind farms do. But you just kind of get a sense of how much things are changing, like the magnitude of change that we're living through right now. Okay, now I'm going to wind up the end of this presentation. I'm really going to talk about where I think we need to focus. And this is the Market Fairy. So I don't know if folks have met the Market Fairy before, but she's lovely, and she can solve all of our problems. Basically, we don't have to do anything because the market just fixes all these problems by itself, and we don't have to worry about anything. That was really an approach that we believed in fervently, you know, for probably 20 years as we were thinking about how this industry was going to launch. And the issue is that we were on a larger scale had gotten so used to thinking about markets, and we had even started calling them magical, you know, to sort of use Reagan's terminology for these things, that we lost track of what it means to build out large scale infrastructure and sort of how this works. And so there are these very particular aspects of our infrastructure that we depend on. You know, I love how Elizabeth Warren talks about these things, that you know, a lot of these, the roads you drive on and the schools that people go to, you know, we take them for granted, but this is our infrastructure. These are our public assets that we build for the public good, and they don't just emerge spontaneously out of markets. And so Massachusetts learned, if we're going to have a market, if we're going to have price signals, if we're going to stimulate an economy that grows and supply chain, these things need to be framed. They need to be they need to be framed in an appropriate way, and then they need to be regulated so that they actually function in a manner that's in the public interest. So I'm going to talk about infrastructure, supply chain, and transmission, and how we think long term, and some ideas that we're interested in terms of pursuing this as we develop an offshore wind market that also we try to develop in a manner that is consistent with our public interest, and namely something that helps us to realize our social and environmental ideals. So I'll start with infrastructure. You know, this is so these are some colleagues of mine, and we have the privilege of monitoring these turbines, both at the Block Island Wind Farm and at the Seavow Wind Farm, and hopefully soon to be some other wind farms, to try to monitor them. When they come to the end of their life, we're going to need a record of all of their stresses and strains in order to recertify and repower them and make them last longer. And believe me, when we get to the end of life of these turbines, just like our buildings and bridges and other assets, people are not going to want to tear them down. They're going to want to keep them around, and they're going to want to continue to use them because, to Pamela's point earlier, the energy is going to be very inexpensive by that point. This is the Hoover Dam. The Hoover Dam is almost 90 years old. To my knowledge, no one's planning on tearing it down anytime soon. And someone had asked the question about machines lasting for 100 years. I used to say, well, you know, the dam is still there. They probably replaced the turbines. But then I got to know the Kingsbury Corporation that built the original bearings for the turbine generators in the Hoover Dam. And the same bearings that were installed in the mid-1930s are still functioning at the Hoover Dam. So you actually can design machine parts to last for a very long time. And this is some cutting edge research that we're doing with GE and Kingsbury and NREL and colleagues in the UK right now to bring fluid film bearings to offshore wind. So it's a very exciting project. Let's talk a little bit about offshore wind foundations. You folks may be familiar with a monopile. It's like, I think of it like a beach umbrella or a big fence post that you hammer into the ground. It's a sort of a hollow tube that's now 10 meters in diameter. Really fascinating marvel of engineering. These are kind of the de facto, you know, foundation of choice. Then you get a jacket. A jacket is a truss structure. You can have jackets that have pin piles at the bottom, again, piles that you hammer in, or you can have suction buckets. This one shows a suction bucket. And then on the far left, You have a gravity-based foundation, which I think of as like maybe a Christmas tree stand or one of these stands that you put a patio umbrella in, and you can float it out, and then you can fill it up with ballast and sink it down to the bottom, and it's a self-stabilizing system. We have a lot of options for how we design these foundations, and there's room for engineering creativity to think about how do we want to do this in the United States. This is a recent article in the Connecticut Examiner from a couple of years ago featuring a wind farm in France. These foundations were installed by a gigantic crane. They were not floated out, but you can see there's a Norwegian company that we were working with that was developing float out solutions. We do have problems right now with our wind turbine installation vessels. There are not enough vessels in the world to install the wind turbines in the United States, let alone worldwide. And so we need other forms of construction. So we could actually be designing these to float them out. When you float them out and you sink them, it's a lot quieter. We're not making as much noise as driving the monopiles. That's going to be better for the marine mammals, better for the whales. And it turns out that when you build these things out of concrete, you can build them out of low carbon concrete that has a lower CO2 emissions content than steel. And you can also employ somewhere between 10 and 30 times as many people, because it turns out that concrete, the materials are cheap and the labor is expensive. So if we want to employ people, concrete is a very good material to work with, and we can design it to last for 100 years. So these are kind of creative solutions that we haven't had the courage to try yet because we're early days in the industry. But if we can gather our courage and if we can prototype new solutions here, there are ways that we can innovate, we can lead, and we can really do things that are going to make a difference in terms of the jobs and the protecting the environment, like we talk about. This is a Spanish approach. These engineers in Spain are fantastic engineers, and they've literally developed turbines where you put the entire turbine together at port, you float it out, and then you can, through a telescoping platform, you can position it on the fixed bottom. And so people draw distinctions between floating offshore wind and fixed offshore wind. But I like to think about float out solutions as let's figure out how to build these things at the port, float them out, and we can either sink them or we can tether them. But this is an entire class of foundations that we could be developing. It's really ripe for engineering innovation and exploration. Very exciting technologies to be exploring. And so if we think about putting all of this together, this is a vision for what we might think of as future offshore wind foundations. Foundations that are quiet and foundations that are deliberately designed with their chemistry and their geometry to become artificial reefs that support biodiversity, that actually promote the growth of fisheries, that are designed to support certain habitats. We have long experience watching hardscapes get installed in the ocean with no intention of supporting marine life, becoming these marine sanctuaries. And so in this is the key to thinking, the ocean, at least our coastal waters, it's not so big anymore. And we have this massive aquarium out there that we're really not taking good enough care of. How do we take better care of it? And how do we think of this as a place where, as we are building out this infrastructure, we're doing it with a sense of environmental stewardship that really is bringing the ocean back to life and caring for our fisheries and caring for our marine species? This is where we need to be focused. And this is an opportunity for New England to become a world leader. I'm going to talk about supply chain just very quickly, then I'll hit transmission, and then we'll be done. We'll have 15 minutes for conversation. Supply chain, again, just to remind folks, this is kind of how Tufts got involved in this. As I was involved in the design, both of the Marine Commerce Terminal and with Tony on the Wind Technology Testing Center. And as we saw these early infrastructure projects, we realized, this isn't just about the turbines. We're going to need dozens of ports. We're going to need dozens of laboratory facilities. We're going to need a lot of this. And how do we pull this together in a way that can sustain an energy transition? And so we started thinking about everything, like we say sometimes, everything that's not painted white. What about all the other stuff that's not the turbine, the transmission, what's underwater, the infrastructure, the policy? And that's what we've been focused on. And it's a very compelling area. We really enjoy being engaged in that way. Little note on supply chain here. This is the Block Island turbine. It's a 6 megawatt turbine. It's kind of small by comparison to a 15 megawatt turbine. You can see the really big European wind installation vessel installing the turbine. By comparison, you can see an American flagged vessel to the right. It's one of our largest jackup barges at the time. And you can just see that we do not have the installation vessels to install these turbines. They're building the Charybdis in Brownsville, Texas right now, Dominion Energy is. And so we've got one, but we're going to need 5 of these in order to build out the 30 gigawatts by 2030. We're also going to need to see, as you see on the right-hand side, we're going to need to invest about $7 billion in the next 2 or 3 years to be able to realize the 30 gigawatts by 2030. So again, we're not going to have a market unless we create a market. We're not going to have a supply chain unless we create a supply chain. It doesn't make sense to create a supply chain on the backs of individual projects. And for the first time in decades in this country, we're talking about industrial policy through the CHIPS Act, the Inflation Reduction Act, the Jobs Act, and we're really going to need to be thinking about this. And this is the kind of a project that's going to happen both at the state and federal level, because energy policy is a state level issue. But industrial policy is sort of a combined federal and state policy at this point. And so we're at this time where it's really compelling the opportunities for collaboration between the state and federal levels to be thinking regionally about these issues. All right, I'm going to move into transmission and then we're done. Just a few slides. This is a notion of an offshore wind transmission backbone. What's important about this is when you look at the blue lines on this map, these are the 500 kilovolt lines. There aren't that many of them, and there aren't that many places to come ashore. If you look at New York and New England, you'll see the purple lines. Those are the 345 kilovolt lines. Those are about half the capacity of the blue lines. We have a lot of these in New England. If you look at New York is kind of landlocked. There aren't that many places to get into New York. Under the Verrazano Narrows Bridge, that will quickly become quite crowded if it's not coordinated. And so this question of how do we coordinate these and how do we coordinate the points of interconnection is a really central question to cutting edge research. This is an image that we developed in conversation with the National Renewable Energy Lab in 2022. The goal is to minimize the environmental impact by engineering the grid in such a way that we maximize the capacities of the landing points. Right now in New England, you can land with about 1,200 megawatts. We're talking about increasing that by a factor of 10 or 20 in the next 20 years to have super high capacity corridors on what's called a macro grid so that we can deliver this electricity and use it in this new renewable paradigm. I'm just going to look very closely at landing number 5. This is the New Jersey State Agreement approach. And this is an analysis we did with a commercial grade software where we concluded very similar conclusions to what resulted from the New Jersey State Agreement approach, which basically wound up developing about a 5 gigawatt corridor, plans for a 5 gigawatt corridor through the Larrabee substation up through Smithburg and Deans. This is one of these very high capacity power corridors where it is essentially less expensive than most other places on the East Coast to come ashore, to reverse power flows and to use the existing infrastructure. So there's all sorts of really interesting creative potential up through about the first 30 to 70 gigawatts of offshore wind to use what we have. But then once we tap that out, we're going to have to start connecting things together into this larger grid. And so this is a project that we've been involved in for several years with Clemson and Iowa State, developing several models. You see model 1, 2, and 3. Model 1 is a 90,000 bus commercial grade model. Model 2 is a 1,000 bus model. And now model 3 is a model of the entire country with the macro grid. From an engineering point of view, you need all of these different perspectives to be thinking about this problem creatively and for them to be interacting. So here's kind of what model 1 looks like. It looks very complicated. Here's what model 2 looks like. It's a more comprehensible and easier to understand, reduced grid that we can iterate on through more cases. What we learned from that model can then be brought back to model 1 for a few analyses with this idea of then in model 2, we're developing, well, what would the offshore grid look like? That's what you see the black lines. And so these are some recent results of model 2. And the green lines over here on the left are sort of, this is all an emerging technology. The model is cut off at this point. We don't have the boundary conditions appropriately set up to go into the rest of the Eastern Interconnect. So don't take these lines incredibly seriously, but watch out for these lines. As you go to 30 gigawatts, where does the offshore grid want to start to connect to itself and where does it want to connect into? It wants to connect into load centers. If you go to 2036 and 60 gigawatts, you can see it coming through Long Island Sound. You can see the floating offshore wind wanting to go straight into Boston, and you can see the grid wanting to start to form. You go to 100 gigawatts by 2041, the grid grows out a little further. 2046, if we go to 200 gigawatts, in 2030, by 2051, if you get to 300 plus gigawatts, I believe this is about 300 to 368 gigawatts of offshore wind, you can see where the reinforcements want to happen. And again, it makes a lot of sense. The power wants to go to load. And so we need to develop an offshore grid, has one permitting authority, the federal government, at least when you're 3 miles offshore, that can be developed. We need to have an offshore Power Systems Administration that administers this offshore grid and actually runs the controls of it. It'll be high voltage DC, so it's controllable. It'll come ashore. And when it comes ashore, how do we connect this into the rest of the country through this macro grid? And so for a long time, people thought the macro grid was going to go from the inside of the country to the outside. But with the permitting challenges and the supply chain challenges of getting underground HVDC, the offshore wind industry might actually be the place that solves these problems. And I've been thinking that the offshore grid off our coast might be the first leg of the North American macro grid. So with that, I'll conclude the presentation. I'll stop sharing for the moment, and we can move back into the final round of questions. Tony, I'll follow your lead.
Sorry, I was on mute. And I'm also, the end of your presentation suddenly seems to have moved, there you go, hidden my my chat screen. And so let me start. Roy, you had a question, and it's a little bit of a long one. Having gotten through this far through the presentation, maybe you could try it again, explain exactly what your question is.
Actually, I have another question. I don't know how many I'm entitled to, but I'd like to ask on a different subject. First, let me thank you for your fantastic presentation. Very, very informative. I'm just wondering about the pricing of the PPA contracts. Who negotiates the price? Who pays the price? How does it relate to the wholesale market that the ISO operates? So my understanding is that the states negotiate the prices with the project developer, and then I assume that there's a contract for difference that the utility, the Eversource of the world would pay, so that the utilities would buy the electricity on the ISO wholesale market, and then whatever the difference is between, say, the $20 per megawatt hour they pay right now versus the $150 a megawatt hour that the state might negotiate with the project developer, they would pay that to the project developer. Just wondering if you can explain how that all works.
So that's negotiated currently through the Massachusetts Department of Energy Resources. The Massachusetts law has evolved and changed, over the last several years. And right now the DOER is responsible for ultimately selecting, the prices are submitted in a competitive solicitation. Prices are selected, and then there's a negotiation and an award made. And so those are generally in Massachusetts power purchase agreements. Ultimately, you can think about pricing, even though people talk about it in different ways in New York, New Jersey, and Massachusetts. You can put it onto a similar footing, and we wrote a paper to help people understand that in recent memory. Interestingly enough, wholesale prices, at any moment, you can always open up ISO to go and see they're at $20 a megawatt hour. But there was a moment in August of this year where prices hit $2,700 a megawatt hour. Everything was red. It was like a different color than that thing ever lights up in. And in the spring of 2022, I calculated that the average wholesale price was $95 a megawatt hour. We were regularly getting up above $200 a megawatt hour in February of 2022. So prices fluctuate, wholesale prices fluctuate a lot, which is why, we pay retail and these things are stabilized. And in terms of how prices are set and how rates are made, this is something that I really believe needs a lot more transparency and public understanding of, so that we can think about this. These are things that we have the capacity to understand. but we need to develop the language for understanding them, much in the same way that we have the capacity to understand how the grid works, and we need to develop the language for understanding that. So I see that. I love your question and I love your thoughts. And really, I see a lot of what we're doing when I think about this from our program's point of view and from an intellectual point of view. We are in the process of creating a language that can help us deliver the energy transition, because it's this language that becomes the medium in which we do all of this creative work. And we're piecing it together from all these different parts of the world.
Great. Well, thanks so much, Sam.
Tony Lee, why don't we go to you, and then I'll go to Pamela, and then Thomas.
Thank you very much, Eric. This has been very informative. I was wondering if you could talk a little bit more about transmission and the cable lines. And did I see where China is considering negotiating with Chile to put solar panels in Chile and then have a 9,000-mile cable to bring the energy to China?
I haven't heard of that. That sounds like an ambitious project. I think that it brings up this question of how do different regions, understood broadly in the context that you just mentioned it, decide to share power. And it kind of makes me think of for a long time people have looked at places like the Sahara Desert and said, well, my God, you could power the entire world off of the sunshine in that part of the world. And so I think the question really, that is the name of the energy transition, is these renewable energy resources are very powerful in certain parts of the world, but those parts of the world aren't always close to load. And so transmission becomes the physical connection between these various parts of the world. And we're going to need to have transmission that functions in a new way and at a new level. And I'm not a power systems engineer, but I work with a lot of power systems engineers. And my understanding is we have the technology to deliver this through high voltage DC, through multi-terminal, but we need to be doing the equivalent of building a lot of wind technology testing centers to be testing all of these things, trying them out, testing them to failure in safe places so that we know exactly how all of this functions. We get the circuit breakers functioning, we get the voltage source converters, and we're moving into this new technology. I think it's an incredible opportunity for American manufacturing as we think about reshoring in this part of the world. If you want to buy HVDC technology right now, you have to get in line in Europe and wait until the 2030s. So there are a lot of opportunities in transmission, and for us to be talking about it in these different ways.
Pamela?
Hi, thank you. I just wanted to point out that I put a couple of links in the chat about long-term seasonal battery storage. Two important ways we can do it is, one, we can store it as heat in sand, giant sand pits. Another is we can liquefy air the way we liquefy natural gas and store energy for as long as we want, cheaply with already discovered technology. We don't have to do the lithium stuff. That argument is fossil fuel company divide and conquer nitpicking. But it's important for all of us to know how the systems interact, because we have to make massive changes. I think we need to use economic arguments and include the costs, not just the costs of doing it, but the costs of not doing it. Nobody uses the costs of not doing it. I wish somebody would figure out what the costs of the major destructive storms that we never thought we'd have, like starting with Katrina, that destroyed New Orleans, and the massive wildfires and the floods and so on, because those we all pay for. The insurance, in the coastal areas, the costs of not doing this are so high, and they're ignored, as well as the massive subsidies that the fossil fuel industry has had for 100 years, that the um, wind and solar industry has not had and should have. We pay massively for our own destructions, and we need to lobby Congress to take the darn tariffs off solar panels. What kind of stupid country? We should welcome China dumping solar panels on us. Take them at the cheapest prices.
Pamela,
Yeah,
Pamela,
I'm
can we just have Eric comment on that a sec? And then I want Thomas to ask the last question.
Well, I mean, Pamela, when you say it, it's so clear. It makes one wonder, why don't we already have a rigorous, widely understood language for talking about all of this? You know, it's sort of incredible, honestly. And we need a language for talking about things that are in our long-term interest. And I think that's been a very hard thing to get to, especially in the last 40 years in this country. So I think I feel like we're coming into a new time where we're talking about economics in a new way, you know, and in a way that actually is more consistent with world historical phenomena and, you know, all of a much broader perspective. So
modern
I'm hopeful that we'll
monetary
find
theory.
there'll be
Truth.
some emerging economists who help us figure out how to speak this new language.
Stephanie Kelton.
So, Eric, do you have time to answer one more question?
Certainly.
Oh, okay. I know you had to move your next meeting, so that's
Oh,
why
yeah.
I was
Well, at
asking.
this point, a couple minutes either way would be okay. Thank you for asking, Tony.
Yeah, you're welcome. Thomas.
This is just a great experience for me as a layman to learn about the technology that is driving this wonderful revolution in power production and use. But I guess I am tied to the notion that you got to focus on what's the cost for the retail user of the power.
Yeah.
That's going to be the big driver. And if we try to take our eyes off that with a lot of other stuff, it ain't going to work because people want cheap electricity. So to me, I always look at this stuff in terms of cost per kilowatt hour. So it looks to me like Vineyard One has come in at a cost of around 6 cents per kilowatt hour, if I'm correct. And that is a really good cost. If you look at the previous round on the Cape Wind, the cost started at 18 and rose to 31 per hour. Right. My question really focuses on why do we want to enter into long-term fixed price contracts for the whole shebang now? It seems to me two factors are playing the game here. One is the improving technology over time. We're going to have more efficient turbines. We're going to have more efficient methods of installing them. We're going to have more efficient methods of conveying the electricity. So all of these changes are going to be constantly changing the cost. So you maybe not want to go for 30 years on this stuff or 100 years on this stuff. That's kind of looking at the old type of coal and gas generation idea. So be flexible so that you can take advantage of the increasing efficiencies coming out of these continuing changes in the technology. And the second piece is right now, we're at the high cost period. We're short of labor. We have supply chain problems, and we don't have enough construction vessels, and interest is high. Now that's going to pass. So would it be a good idea to also say if you're going to do 1,000 gigawatt purchase from a developer, to do it in tranches? So we'll agree on 1,000 gigawatts over time, but let's take a 200 gigawatt tranche now. And when you get that done, because it's going to take time to build all these, then we'll do the next tranche. And hopefully we'll be taking advantage of a better and more cheaper cost environment as these factors have changed downward, and the technological benefits of more efficient capacities. So I just haven't understood quite why we want to seal up the cost now for 25 or 30 years at today's high price.
Well, the cost right now, even compared to a couple of years ago, rose. And there were concerns that if there was not a purchase of power in this procurement, that the industry, we'd lose our shot at the industry. And so the way that I think about this, Thomas, is that when I think about, again, I find myself thinking on different orders of magnitude. What we're doing at this moment, even though we're talking about 1,000-megawatt projects, is really small compared to what needs to be done. And therefore, the disturbance to the cost structure of our electricity bills is also very small by comparison, and so we may pay higher prices in the moment, but I think the logic is that we're actually talking about whether the industry is going to exist or not, and whether it's going to launch, and are we on our way to an energy transition. Even if we build out the 30 gigawatts, in my opinion, that's only 10% of where we need to get to. And as a market forms and as all these transformations happen that you're talking about, they will only happen inside of a system that is functioning where people are gaining experience. And so in the absence of a system that is actually functioning and gaining experience, there will be no improvements. And so the question I think that we're facing right now is a question of how do we launch this? How do we own it ourselves? How do we take control of our own destiny so that we can apply our creativity to these questions? And then, in my opinion, as I watch, just what we do with our buildings and our bridges and our infrastructure, we tend to keep them around. We tend to keep things around that are this big. And so it's not really an added cost to design things for a longer lifespan. One can do this very, very efficiently for numbers that wouldn't even register on someone's electricity bill. And I agree with you. It's the electricity bill itself we need to watch out for. And I think that there's a problem in the way we talk about prices, because people get wholesale prices and retail generation prices mixed up with retail sales, which includes transmission and distribution. And on the one hand, we're talking about 6 cents a kilowatt hour. And on the other hand, I'm paying 35 cents. As a ratepayer, I could care less whether I pay 35 or 36 cents, but it starts to make a difference when I'm paying 25 cents or 40 cents a kilowatt hour. And I just don't think that when we have these conversations that we're distinguishing things in this way. So I come back to this notion of language. How do we know that when we're talking about something, we're all talking about the same thing at the same time? And I think therein kind of lies the excitement and the opportunity. When the first industrial revolution began to unfold in England in the wake of what people call the Newtonian synthesis at the end of the 17th century, and people were excited about mechanical work and heat and going into the 19th century and electricity. This is what people spent their time doing. They spent their time developing and listening to public lectures on physics, and everybody was excited about it. And it was this big phenomenon and everybody was into it. And I think that was the first energy transition. Here we are in another energy transition, really amounting to a major second industrial revolution. I know some people want to say we're on the fifth industrial revolution, but the first one was about energy and this one's about energy, in my opinion. We have got a lot of stuff that we all need to be able to learn and talk about. And so I just really admire what you and your group are doing, and everybody's sort of keeping track of these things and figuring out how to have this conversation, because I think, to embrace it as something exciting is really worthwhile. And I think that this process of deliberation, we've got to have 100 million people in this country who can have this conversation. What is it that people need to know so they can talk about this? I think that's a fascinating question to contemplate and to engage with folks on.
Eric, thank you so much. I want to ask you one more question. Would you be willing, if people have additional questions, they could funnel it to me, for example, and I could send them to you?
Well, maybe, yeah, I think we could do that. Maybe you and I could have a follow-up conversation or something. I think I'm not in a position to I've got too much email volume to
Yes.
email by the onesies. But
Yep.
I'm more than happy to continue this conversation in a way that works for people. So I mean, again, thank you so much for having me with you. And again, it's really nice to meet all of you and to have a chance to exchange thoughts. And just really, I'm an admirer of the work that you all do. So thank you.
Well,
Thank you.
thank you, Eric. Thank you, Tony. This has been just an amazing presentation. I mean, I think we've all learned a lot, and we know that this, you know, we're in this transition, as you say, and we're gonna, you know, there's a lot more to come. So I really appreciate your taking the time today, Eric, and Tony for your moderating the presentation. So thank you, everyone. And Eric, special thanks to you, and really appreciate it.
My pleasure. All right. Thank you. Good
Yeah.
to see you all.
Bye.
Thanks.
Yep.
Bye-bye.